Welcome to this presentation on time-mass duality, a unified framework with natural units. I'm excited to introduce you to a revolutionary approach that bridges quantum mechanics and relativity theory, potentially resolving long-standing questions in theoretical physics. Let's explore how a different perspective on familiar concepts can lead to profound new insights. At the core of this framework is a remarkable duality. We present two fundamentally different yet mathematically equivalent descriptions of reality. The T0 model features absolute time, variable mass, and an intrinsic time field Tx. The extended standard model maintains relative time and constant mass, but extends them with additional terms. Though conceptually opposite, both yield identical physical predictions, a mathematical equivalence that offers profound flexibility in how we approach physical problems. Let's compare these approaches with standard physics. The standard model treats time as relative, dilating with velocity and gravity. Mass remains constant, and gravity manifests as curved spacetime. The T0 model inverts this completely. Time is absolute while mass varies with the Lorentz factor. Gravitational effects emerge not from curved space, but from the intrinsic time field. The extended standard model preserves conventional concepts, but adds terms that produce identical predictions to the T0 model. A fundamental shift in our approach. While conventional cosmology relies on empirical measurements and data fitting, our framework reveals a profound hierarchy of derivations, all traceable to energy as the foundational quantity. The Planck constants length, time, mass, and temperature form the primary level of this hierarchy, emerging naturally when we set Planck's reduced constant, speed of light, gravitational constant, and Boltzmann constant to unity in our natural unit system. From this foundation, a second level emerges where electromagnetic constants like vacuum permittivity and permeability are no longer independent, but derived directly from the primary level. The Coulomb constant, which determines the strength of electric interactions between charged particles, becomes a simple mathematical consequence, rather than an empirically determined value. The fine structure constant, conventionally approximated as 1/137th or about 1/137, has long been treated as a mysterious value that simply must be measured. Physicists from Feynman to Eddington have speculated about its significance. But in our framework, this value emerges naturally as a direct consequence of how electromagnetic interactions relate to quantum processes. When we set our natural units properly, this constant equals exactly 1. Revealing that its traditional value is simply an artifact of our arbitrary measurement systems, rather than a fundamental mystery. Similarly, the Kappa parameter crucial to our modified gravitational equation isn't introduced by hand, but precisely derived from Higgs sector parameters, the self-coupling constant, vacuum expectation value, and Higgs mass. This derivation creates a direct bridge between the quantum realm and gravitational phenomena, unifying previously disconnected scales of physics. When converted back to conventional SI units, all these theoretically derived values match experimentally measured ones with astonishing precision, deviations less than 1 part in a million. This indicates we're uncovering a fundamental unity in nature where constants across all physical domains are manifestations of deeper mathematical relationships. Nothing is arbitrary, nothing is coincidental, and nothing requires magical thinking. All physical constants are expressible in terms of a single quantity, energy. This represents an unprecedented theoretical economy, where phenomena from quantum interactions to cosmic structure emerge from a single unified mathematical framework, without arbitrary parameters or unexplained values. Which framework should we use? The T0 model excels with large rest mass systems, non-relativistic quantum mechanics, and gravitational systems. The extended standard model better suits relativistic particles and high-energy physics experiments. Since both give identical predictions, the choice isn't about correctness but elegance for the specific problem. This parallels how physicists choose between wave and particle descriptions depending on the phenomenon. The foundational equation of quantum mechanics, Schrödinger's equation, has served physics remarkably well for nearly a century. In its standard form, IH bar times the partial derivative of psi with respect to time equals the Hamiltonian operating on psi. This elegant formula treats time as a uniform parameter, applying equally to all quantum systems, regardless of their mass or energy. Traditional quantum mechanics relies on a simple Schrödinger equation where time appears as a uniform parameter. IH bar times the partial derivative of psi with respect to t equals the Hamiltonian operating on psi. In our T0 model, we introduce a crucial extension by incorporating the intrinsic time field Tx. The modified equation now reads IH bar times Tx times the partial derivative of psi with respect to t plus IH bar times psi times the partial derivative of Tx with respect to t equals the Hamiltonian operating on psi. This elegant modification creates a direct mathematical link between a particle's mass and its quantum time evolution, while preserving all the successful predictions of standard quantum mechanics in the appropriate limits. The intrinsic time field varies with mass according to Tx equals h bar divided by mc squared, creating a seamless connection between quantum dynamics and gravitational phenomena through a single unified field theoretic approach. Let me explain this standard model Lagrangian, which encapsulates all the fundamental physics we currently understand. The first term -1/4 f mu nu describes all gauge bosons including photons, gluons, and the W and Z particles that mediate forces. The second term with the psi bar gamma d psi represents all fermions like electrons, quarks, and neutrinos, showing how they move through spacetime and interact with gauge fields. The third term with the absolute value squared describes the Higgs field dynamics, including its kinetic energy and interactions with gauge bosons. Finally, the -v phi term represents the Higgs potential that gives particles their masses through spontaneous symmetry breaking. This elegant mathematical formulation has successfully described virtually all particle physics experiments to date, but critically lacks any connection to gravity. Our extended framework will now show how to incorporate the intrinsic time field into each term, while preserving all these successful predictions. Here we see the T0 extended Lagrangian in its complete form. This mathematical structure represents one of two equivalent ways to extend the standard model of particle physics. Each term in this equation incorporates the intrinsic time field Tx, transforming how we understand fundamental interactions. The gauge boson term now includes a t-squared factor, creating coupling strengths that vary with the time field. This seemingly small modification dramatically transforms how force-carrying particles like photons and gluons interact with matter across different mass environments. The fermion term incorporates our modified covariant derivative that accounts for time field gradients, giving matter particles like electrons and quarks new dynamics in regions of varying gravitational strength. The Higgs terms couple directly with the time field, creating a bidirectional system where the Higgs field and time field influence each other's behavior. This mathematical relationship reveals the deep connection between mass generation mechanisms and gravitational effects, bridging scales from particle physics to cosmic structure. Finally, we've added the intrinsic time field Lagrangian term that governs how Tx propagates and interacts with itself throughout spacetime. These systematic modifications preserve everything successful about the standard model, while seamlessly integrating gravitational phenomena into the same mathematical framework. No additional dimensions, no speculative constructs, and no arbitrary parameters, just an elegant extension that unifies quantum and gravitational physics through a single coherent field theoretic approach. Let me summarize these essential modifications. We've transformed gauge fields with a t-squared factor, creating mass-dependent coupling strengths. We've replaced the standard covariant derivative with our extended version accounting for time field gradients. The Higgs potential now depends on both the Higgs field and time field. Finally, we've added the intrinsic time field Lagrangian governing how Tx propagates and interacts. Together, these preserve standard model successes while seamlessly incorporating gravitational phenomena. What's most elegant about our framework is how gravitation emerges naturally from Higgs field and time field interaction. Rather than assuming curved spacetime as fundamental, we derive it from time field dynamics. The metric tensor emerges as a modification of flat spacetime through the time-field ratio. This produces a modified gravitational potential with both the inverse distance term and a linear term proportional to kappa. This single modification explains both galactic rotation and cosmic acceleration without dark components. Our modified gravitational potential equation introduces a linear term alongside the traditional inverse distance relationship, expressed as phi r equals -gm over r plus kappa times r. This single modification explains what standard cosmology attributes to both dark matter and expansion. What the unextended standard model interprets as cosmic acceleration due to dark energy, our framework explains as a natural consequence of the linear term in our gravitational potential. No expansion is occurring. Instead, light loses energy progressively as it travels through the intrinsic time field. The Kappa parameter isn't arbitrarily chosen. It emerges naturally from our unified energy-based framework, mathematically derived from Higgs sector parameters. This theoretically grounded formulation elegantly explains both galaxy rotation curves and the phenomena misinterpreted as cosmic expansion, without inventing invisible matter or energy. This clarifies that the T0 model reinterprets the same observations through a non-expanding universe framework. This diagram shows the fundamental interaction between the Higgs field and our intrinsic time field. The Higgs mechanism gives particles mass, which then couples directly with the time field. This creates a feedback loop where mass affects the time field, and time field variations influence mass distribution. This explains why massive regions create stronger gravitational effects. Instead of treating gravity as a fundamental force requiring quantum gravity, we show how it emerges naturally from the same framework as other forces, primarily manifesting at larger scales. Our framework predicts a modified gravitational potential, combining the familiar inverse distance term with a linear term proportional to kappa. This single modification reinterprets phenomena traditionally attributed to both dark matter and dark energy. At galactic scales, it naturally produces flat rotation curves without requiring invisible halos. At cosmic scales, this same term creates effects that standard cosmology misinterprets as acceleration due to expansion. Unlike the unextended standard model that views these observations as evidence of an expanding universe driven by dark energy, our static universe model attributes them to intrinsic properties of the gravitational potential. This unified explanation eliminates the need for dark components, while maintaining perfect consistency with observational data, from planetary orbits to large-scale cosmic structure. Our framework presents a fundamental modification to how we understand the relationship between cosmic background radiation and redshift. While the standard cosmological model employs a simple linear relationship, our approach introduces a crucial logarithmic term to the equation t equals t0 times 1 plus z times 1 plus the natural logarithm of 1 plus z. This modification arises through two distinct physical interpretations in our dual frameworks. The T0 model attributes this logarithmic component to energy interactions mediated by the intrinsic time field as radiation traverses cosmic distances. Meanwhile, the extended standard model derives the identical mathematical relationship through an entirely different mechanism: light deflection through modified spacetime geometry. This remarkable convergence on the same formula despite different underlying physics demonstrates the deep mathematical equivalence of our dual frameworks. The addition of this logarithmic term significantly transforms our understanding of cosmic thermal history compared to conventional models. It suggests a fundamentally different evolution of background radiation throughout cosmic history, potentially resolving several anomalies that standard cosmology struggles to explain. The specific temperature values and numerical predictions that emerge from this equation will be examined in the following discussion, where we'll explore how this modifies our understanding of key cosmic epochs. Let me walk you through one of our most testable predictions: wavelength-dependent redshift. The precise formula is z of lambda equals z naught times 1 plus beta t times the natural logarithm of lambda divided by lambda naught. The parameter beta t has a specific value of approximately 0.008 in standard units. This produces a very clear prediction. Redshift will vary by about 2.3% for every tenfold increase in wavelength. What makes this especially valuable is that it's directly testable with current technology. The James Webb Space Telescope can perform high-precision spectroscopy across a wide wavelength range, from 0.6 to 28 micrometers. When observing the same distant quasar or galaxy, emission lines at different wavelengths should show systematically different redshift values following our predicted pattern. This sharply contrasts with standard cosmology, which requires identical redshift regardless of wavelength because expansion affects all wavelengths equally. There's simply no mechanism in conventional models that would create wavelength-dependent redshift. This provides perhaps the cleanest experimental test between frameworks. If observations reveal the specific wavelength-dependent pattern we predict, it would strongly support our model over conventional cosmology. The technology exists today to perform this crucial test, requiring only careful spectroscopic analysis of existing celestial objects. The logarithmic term in our temperature-redshift relationship fundamentally transforms our understanding of cosmic thermal history. Using our formula T equals T0 times 1 plus Z times 1 plus natural logarithm of 1 plus Z, we calculate a dramatically different cosmic blackbody radiation temperature. For the recombination epoch at redshift 950, our dual framework predicts a temperature exceeding 24,000 Kelvin, about 8 times higher than standard cosmology's prediction of 3,000 Kelvin. This dramatic difference emerges when we express our equations in natural units where beta T equals 1, which is mathematically equivalent to beta T approximately 0.008 in SI units. They represent identical physics despite their different numerical values. Both frameworks predict the same observable 2.725 Kelvin for today's cosmic microwave background. The recalibration from standard cosmology's redshift 1100 to our framework's redshift 950 for the recombination epoch emerges naturally from our mathematical structure. The physical conditions required for hydrogen recombination, around 3000 Kelvin, occur at this revised redshift value when calculated using our temperature formula. This single cohesive modification provides elegant explanations for several cosmic microwave background anomalies that have persistently challenged the standard cosmological model. Let me summarize the key differences in cosmic microwave background predictions between standard cosmology and our dual framework. The standard model uses a simple linear relationship where temperature equals T0 times 1 plus Z. Our framework adds the crucial logarithmic term, giving us temperature equals T0 times 1 plus Z times 1 plus beta T times natural logarithm of 1 plus Z. This creates dramatic differences in our understanding of cosmic thermal history. At what standard cosmology identifies as the recombination epoch around redshift 1100, their model predicts temperatures of approximately 3000 Kelvin. Our framework predicts dramatically higher temperatures of around 24,000 Kelvin for this same period, nearly 8 times higher. This isn't a contradiction but requires recalibration. The physical conditions necessary for hydrogen recombination around 3000 Kelvin would occur at a different epoch in our framework, approximately redshift 950 rather than 1100. Both frameworks perfectly predict today's observed cosmic background temperature of 2.725 Kelvin, but they trace entirely different cosmic histories to reach this point. This demonstrates how a single mathematical modification creates a comprehensive alternative interpretation of cosmic evolution without requiring additional hypothetical components like inflation or dark energy. A fundamental point: all standard cosmological measurements were designed, collected, and interpreted through the expanding universe model. This doesn't invalidate the data, but means we must recalibrate every parameter within our framework. The Hubble constant, galaxy redshifts, cosmic background radiation, and the timeline of structure formation require fresh analysis. In our model, all parameters can be calculated theoretically rather than just measured. What we observe remains valid. A galaxy's redshift is still the same number, but its meaning for cosmic history changes dramatically, potentially solving persistent problems like the Hubble tension. Our wavelength-dependent redshift formula offers testable predictions with current technology. Our CMB temperature calculations suggest higher primordial values, potentially resolving standard model tensions through an elegant mathematical framework. Importantly, when interpreting cosmological data, we're doing so through a theoretical lens. Standard cosmology views redshift as expansion, while our framework sees it as energy loss through the TX field. Both interpretations fit the same data, but with different underlying physics, similar to wave-particle duality in quantum mechanics. I must emphasize this crucial point. Virtually all cosmological data has been collected, analyzed, and interpreted within the standard model framework. This doesn't invalidate the measurements themselves, but requires a comprehensive reinterpretation of their meaning. The Hubble constant, redshift measurements, CMB temperature, the age of the universe, and the timeline of structure formation all need recalibration within our dual framework. This represents an opportunity to resolve existing tensions like the Hubble constant discrepancy, not by discarding data, but by viewing it through a more coherent theoretical lens. Here we see a crucial difference in how we understand the Hubble constant. In standard cosmology, the Hubble constant is empirically measured from observations of distant galaxies. Astronomers measure redshifts and distances, then determine the expansion rate from this data. But in our dual framework, both the T0 model and extended standard model calculate the Hubble constant directly from theory using the formula H0 equals c times z divided by d. This represents a fundamental shift from observation-based to theory-driven cosmology. The calculated value approximately 70 km per second per megaparsec matches observations perfectly, but emerges naturally from our equations rather than requiring empirical fitting. Instead of measuring cosmic expansion and inferring dark energy, our framework directly predicts the observed redshift-distance relationship from first principles. Our wavelength-dependent redshift formula offers testable predictions with current technology. Our CMB temperature calculations suggest higher primordial values, potentially resolving standard model tensions through an elegant mathematical framework. Importantly, when interpreting cosmological data, we're doing so through a theoretical lens. Standard cosmology views redshift as expansion, while our framework sees it as energy loss through the Tx field. Both interpretations fit the same data, but with different underlying physics, similar to wave-particle duality in quantum mechanics. Let me outline specific tests that could validate our framework using today's technology. The James Webb Space Telescope can directly test our wavelength-dependent redshift prediction by examining emission lines from distant quasars across its spectral range. Our modified gravitational equation predicts galaxy rotation without dark matter, testable with current galaxy surveys. Upcoming missions can analyze tiny spectral distortions in cosmic background radiation that differentiate between temperature relationships. Within 5 years, we could have definitive evidence distinguishing between competing cosmological frameworks, potentially transforming our understanding. Both versions of our dual framework make identical predictions challenging standard cosmology. We describe a static, eternal universe without a beginning, no Big Bang in our model. Our modified gravitational equation includes the traditional inverse distance term and a new linear term, explaining both galaxy behavior and cosmic acceleration without needing dark matter or energy. We uniquely predict wavelength-dependent redshift and calculate a different CMB temperature relationship with a logarithmic factor. These aren't adjustable parameters but mathematically derived predictions emerging naturally from our framework. Let me provide a realistic assessment. Our model is recently developed, and no experiments have specifically tested its unique predictions yet. We're presenting a conceptual framework with strong mathematical foundations, rather than an empirically validated theory. That said, our approach maintains consistency with existing observations while offering fresh interpretation. The mathematical formulation is complete and internally consistent, generating specific, quantitative predictions. Some preliminary analyses show promising alignment, but we need dedicated experiments specifically designed to distinguish between our model and standard cosmology. Looking forward, we've identified several specific experiments that could definitively validate our framework. The James Webb Space Telescope could conduct dedicated spectroscopic surveys of distant quasars, measuring multiple emission lines across wavelength ranges to detect our predicted variations. For cosmic background radiation, detailed spectral analysis could focus on tiny distortions that would appear differently depending on which temperature-redshift relationship is correct. Advanced galaxy surveys could map rotation curves without assuming dark matter, directly testing our modified gravitational equation, while gravitational lensing observations could distinguish between standard dark matter models and our framework. At extreme limits, our models reveal fascinating interpretive differences while maintaining identical predictions. In standard physics, as velocity approaches light speed, mass increases toward infinity while time progressively slows. This creates a natural boundary. Objects with rest mass cannot reach light speed. The T0 model flips this perspective. Time remains absolute, but the intrinsic time field approaches zero as velocity increases, while mass increases per the Lorentz factor. Though interpretations seem contradictory, both frameworks predict exactly the same observable phenomena and create the same physical boundary, preventing superluminal travel. What happens when we mathematically explore beyond the light speed boundary? In standard relativity, exceeding light speed creates imaginary numbers. The Lorentz factor becomes imaginary, leading to meaningless imaginary masses. The T0 model faces similar challenges. Beyond light speed, the intrinsic time field would become negative, suggesting some form of time reversal. Both frameworks agree. The superluminal region represents a purely mathematical extension without physical reality. Yet these explorations remain valuable for understanding the fundamental nature of the light speed barrier itself. The dual framework reveals fascinating contrasts at extreme mass limits. In the extended standard model, time undergoes extreme dilation near massive objects. Proper time nearly stops at event horizons while mass remains constant. The T0 model takes the opposite approach. Time flows uniformly everywhere, but the intrinsic time field approaches zero near massive objects, causing dramatic mass increases near strong gravitational sources. Despite these fundamentally different interpretations, both frameworks predict identical event horizons, gravitational potentials, and observational effects, showcasing the profound duality at the heart of our theory. The T0 model reveals something profound about the fabric of reality. Physical distances aren't continuous but occur in discrete, quantized scales following a mathematical hierarchy. Starting with the Planck length as our fundamental unit, we discover a precise sequence of stable scales including the T0 characteristic length r, which equals 11 times the Planck length, where 11 approximately equals 1.33 times 10 to the negative fourth power. This quantization continues through the electron Compton wavelength, the Bohr radius, and extends all the way to cosmic dimensions like the universe's correlation length L_T. These scales aren't randomly distributed, but follow specific mathematical relationships governed by dimensionless constants like the fine structure constant and the T0 parameter beta. Most remarkably, between these stable, quantized scales lie what we call forbidden zones, vast regions spanning multiple orders of magnitude, where stable physical structures theoretically cannot exist according to our equations. The gap between r and the electron Compton wavelength spans approximately 19 orders of magnitude, while another forbidden zone of about 3 orders exists between the Compton wavelength and the Bohr radius. What's truly fascinating is that biological structures like DNA molecules, proteins, cells, and entire organisms uniquely occupy these forbidden zones. DNA's diameter falls at approximately 10 to the power of negative 26 Planck lengths, squarely within a forbidden zone. This suggests that life may utilize special stabilization mechanisms fundamentally different from ordinary matter, perhaps involving information-based organization, topological protection, or dynamic stability that allows it to overcome the restrictions that apply to simpler physical systems. This quantization of length scales provides another experimentally testable aspect of our framework. We predict specific clustering of stable structures at these quantized scales, with relative voids between them, a pattern that should be observable across phenomena from particle physics to cosmic structure. The T0 model offers profound reinterpretations of quantum phenomena. While standard quantum mechanics relies on instantaneous collapse and observer effects, our framework explains these through the intrinsic time field. What appears as instantaneous wave function collapse becomes a natural consequence of absolute time combined with field-mediated mass variations. Quantum entanglement is reinterpreted as correlation through shared time field history, rather than mysterious instantaneous connections. This approach satisfies Bell inequality tests without requiring spooky action at a distance, providing a more intuitive explanation for quantum phenomena. Our framework offers a revolutionary perspective on quantum mechanics. Instead of Copenhagen's observer-dependent collapse or many-worlds branching universes, we present quantum phenomena as field-mediated interactions through the intrinsic time field. The apparent randomness in quantum measurements stems not from fundamental indeterminism, but from interactions between measurement apparatus and the object's time field. These interactions produce predictable mass variations, rather than mysterious wave function collapse. When measurement occurs, the intrinsic time field Tx around the particle adjusts, causing corresponding mass changes according to our fundamental relationship m equals h bar divided by Tx times c squared. While the initial correlation between entangled particles establishes instantaneously within their shared creation light cone, the actual measurement effects remain bound by light speed causality constraints. This framework naturally explains the measurement problem, wave-particle duality, and quantum tunneling through a single coherent mechanism, while maintaining all standard quantum mechanics successful predictions. It resolves the apparent conflict between quantum non-locality and relativistic causality, without requiring multiple worlds or observer-induced collapse. The T0 model provides a novel perspective on quantum entanglement, resolving the Einstein-Podolsky-Rosen paradox that has troubled physics for almost a century. Rather than requiring spooky action at a distance, entangled particles share a common intrinsic time field history established during their joint creation. This creates correlations maintained through absolute time, regardless of their spatial separation. When one particle undergoes measurement, local interactions cause its mass to change through time field variations. Its entangled partner exhibits corresponding behavior not through faster-than-light signals, but through predetermined shared field properties established at entanglement. Initial correlation exists at creation within a common light cone, while subsequent measurement effects propagate no faster than light speed, preserving Einstein's locality principle. This approach satisfies Bell inequality tests, while maintaining both locality and determinism. What appears as mysterious instantaneous influence across arbitrary distances becomes comprehensible as correlated field dynamics with proper causality constraints. By reinterpreting mass as a dynamic property determined by the intrinsic time field, we transform quantum weirdness into intuitive, visualizable physical processes governed by well-defined field equations. The T0 model elegantly resolves several persistent quantum puzzles. The double-slit experiment's wave-particle duality becomes a natural consequence of the intrinsic time field's interaction with matter, with interference patterns emerging from field fluctuations rather than abstract probability waves. Quantum tunneling occurs through local time field variations that effectively change the particle's mass-energy relationship at barriers. Most significantly, the Schrödinger's cat paradox dissolves when we recognize that macroscopic and microscopic systems differ only in their characteristic time field values. This transforms seemingly mysterious quantum effects into comprehensible field phenomena. Our dual framework challenges fundamental assumptions about reality. If two completely different descriptions, one based on absolute time with variable mass, the other on relative time with constant mass, produce identical predictions for all experiments, what does this reveal about the limits of scientific knowledge? This situation parallels wave-particle duality, where light behaves as either waves or particles depending on the experiment. Neither description captures the complete truth, yet both are necessary for full understanding. This perspective invites humility about our theories. Even this elegant dual framework doesn't claim to represent ultimate truth about reality. All mathematical models are approximations that work well within their domains, but inevitably reach limits at extreme conditions. Scientific progress requires this humility about theoretical limitations. Throughout history, frameworks from Newtonian mechanics to quantum field theory have provided increasingly accurate approximations, but each remains incomplete. Our approach offers powerful tools for understanding cosmic phenomena and potentially unifying quantum mechanics with gravity, but we don't claim to have discovered final truth. In evaluating scientific theories, what ultimately matters most isn't whether a framework makes claims about the true nature of reality, but whether it makes accurate, testable predictions. This approach parallels Niels Bohr's perspective on quantum mechanics. The goal of science isn't to reveal what reality really is, but to describe what we can systematically observe and predict about nature. A theory should be judged primarily by its predictive success, mathematical elegance, and problem-solving capacity, rather than by how it aligns with our intuitive notions of reality. Two mathematically equivalent methods to physics that defy accepted wisdom are offered by the Time-Mass Duality framework. Both versions, the T0 model and extended standard model, make identical predictions that differentiate them from standard cosmology. Perhaps most fundamentally, they describe a static, eternal universe without singularities, no Big Bang beginning and no infinities at black hole centers. The real power of this approach lies in its theoretical elegance and its capacity to bridge quantum mechanics and relativity through a single unified framework. For complete mathematical derivations and detailed explanations, visit our GitHub repository. Thank you for exploring these revolutionary concepts with us today.